Powder metallurgy is the application of the principle that metal powders can be processed to make metal parts of unique character. In the basic powder metallurgy process, as it has been developed in the laboratory, metal powders, mixed according to formula, are compacted under great pressure and subjected to heat to produce a metallic material, frequently in finished product form. Powder metallurgy is thus employed to make a wide variety of industrial products. It provides the means of combining essentially non-alloyable metals, combining metals and non-metallic materials, utilizing metals with melting points too high for casting, fabricating metals to obtain unique structural properties, and replacing machining operations in mass production to save time and material. One of the most striking applications of powder metallurgy is the porous self-lubricating bearing, a bearing which carries and distributes its own oil supply by virtue of a special structural property which only powder metallurgy can produce. The manufacture of a bronze porous bearing illustrates the fundamentals of all powder metallurgy technique. The metal powders for the porous bearing are blended according to specification. Each powder is carefully measured by weight. Copper powders are the major constituent of the bronze material specified for the finished bearing. Metal powders differ in the shapes of their individual particles and in the particle size distribution which they contain. Here, various copper powders having different particle characteristics are measured out in the proportions called for. Other ingredients in lesser quantities complete the mixture. Tin powders, which combined with the copper make the basic bronze composition of the bearing, graphite for a secondary lubricant in the finished bearing, and a volatile organic material such as stearic acid for a pore-generating agent. In addition, the graphite and stearic acid will facilitate the forming and ejecting of the powders when they are pressed. This completes the mixture. The powders are now ready for this automatic mixing machine. This machine is equipped with revolving blades designed to achieve a thorough distribution of the metal powder particles. The can containing the powder mix is hoisted into position over the mixing machine. The powders are dumped from it into the mixing chamber, and the machine is turned on. Sufficient mixing time must be allowed to permit a completely uniform blending of the different kind and size of powder particles. After about half an hour in this case, the powders are thoroughly mixed. They are discharged into another container. The powders are kept under cover as much as possible to prevent oxidation and keep out foreign matter. The container is carried into the press room, where this automatic press molds the powders. The powder mixture is charged into a hopper on top of the press. From here it is fed down into a feed shoe which agitates over the twin cavities of the die and fills them. This is a double action press. The powder is compressed from two directions. From above by upper plungers thrusting downward, and simultaneously from below by lower plungers thrusting upward. This double pressing action gives a more even density in the compacted powders than if the pressure were all from one direction. Compressed under pressure of 18,000 pounds per square inch, the powder is ejected in the form of briquettes, 2 at a time. In order to control quality, each run is preceded by a test run. A few sample pieces are run off. They are to be put through a series of quick tests to determine if the press is correctly set. The pieces must be within specified weight limits, an indication of proper density. Next, they are checked for size. The hardness testing machine indicates if they have equal density throughout. And finally, they are tested for roundness. If the samples meet the tests, a full run is started. The briquettes are formed at a rate of 56 a minute, formed to close tolerances in the essential shape the finished bearing will have. The dimensions of the briquettes have been calculated, however, to allow for the change in dimension which may occur during the next operation, the sintering of the briquettes. Sintering is a heat treatment which takes place in this controlled atmosphere electric furnace. It completes the bonding action among the powder particles and creates the porous bearing structure. The furnace has 3 sections. This entrance chamber functions as a preheat chamber, where in this case, the briquettes heat to a temperature of about 600 degrees Fahrenheit. This section is the heating chamber where the actual sintering takes place. Here, the bearing briquettes are brought to their sintering temperature of about 1,500 degrees Fahrenheit. After about 8 minutes in this heat chamber, their sintering completed, the briquettes pass into this long water-jacketed cooling chamber. They are cooled to about 100 degrees Fahrenheit by the time they emerge from the furnace. Trays of briquettes are placed on rollers, which convey them into the entrance chamber of the furnace. The flame curtain, which leaps up as the door opens, prevents air from getting into the furnace, where an atmosphere of hydrogen-containing gas is circulated. The gas atmosphere prevents oxidation of the briquettes and reduces oxide films which were already present on the metal powder particles. Here in this schematic cross-section, greatly enlarged, of part of a briquette before sintering, we see the compacted powders. The dark gray particles are copper. They are in a ratio of about 9:1 to the light gray particles, which are tin. We can see a few small graphite particles, which are black. The other black areas are voids. The stearic acid, present in very small amount, cannot be seen in particle form. It has been smeared in the mixture by the pressing action. Early in the sintering process, even before the briquette leaves the preheat chamber, the tin begins to melt and diffuses into the copper, leaving additional voids. Simultaneously, the stearic acid vaporizes, forming a network of capillary tubes throughout the briquette, imparting a spongy character to the whole structure. As the sintering continues, the diffusion of tin and copper is completed, and the final porous bronze structure is formed. The graphite, distributed in the bronze matrix, has not changed appreciably during the sintering. After slow cooling in the water-jacketed cooling chamber, the briquettes emerge. Here again, a flame curtain prevents air from entering the furnace. Here is how a briquette looks after sintering. It now has the approximate dimensions of the finished bearing. The sintering has caused some distortion, and it is slightly out of round. The briquettes are ready to receive their final dimension and finish. This is done in a sizing machine. Sizing is another precision operation. The briquettes are forced into a die and formed to precision tolerances. This single sizing machine replaces the older machining methods of turning, boring, facing, and reaming. The finished pieces are ejected at the rate of 50 a minute. Sizing has given the bearing surfaces a fine burnished finish, accurate in outside diameter, inside diameter, and length. In addition, serrations have been pressed into the outer surface to fit a splined covering into which the bearing will be inserted. One operation still remains: the impregnation of the porous bearings with oil. The impregnation takes place in this sealed chamber. It is important to pack as much oil as possible into the bearings, filling every pore. A vacuum is created in the chamber, removing the air from the bearing pores. Simultaneously, the vacuum draws oil into the chamber. The oil surrounds the bearings and fills the pores, storing in the bearings their own oil supply for the job they have been designed to do. With impregnation, the manufacturing process is completed and the bearings are ready for inspection. Here is the finished self-lubricating bearing, a precision product made from metal and non-metallic powders. Durable and to the naked eye apparently a solid metal, actually it is a network of thousands of tiny interconnecting pores into which is packed the oil supply, which will flow by capillary action to the bearing's working surface as the work demands. An immediate and uniform oil film is provided over the bearing surface. As the heat on the working surface increases with the speed of the shaft, the oil feeds more rapidly, so that a neat balance between demand and supply is constantly maintained. In this testing apparatus, the shaft turns in a self-lubricating bearing on which is exerted a downward pull of more than 100 pounds. When the shaft is stopped, the supply of oil from the bearing is also stopped. Friction then strongly resists any effort to slide the bearing along the shaft. But when the shaft revolves, it creates heat, which again induces the flow of the oil stored in the bearing. With the resulting oil film, the merest touch can now slide the bearing along the shaft. These bearings and their original oil impregnation frequently last the life of the machinery in which they are used. They are one of many diverse products which powder metallurgy is contributing to modern technology.